Picture a single thread of starlight. It leaves a star, some sun that isn't ours, and crosses an ocean of empty black for a very long time. Nothing touches it. And then, right at the end of its journey, the last sliver before it reaches us, it grazes the edge of a planet. It passes through a thin shell of that planet's air, its dawn, its haze, whatever weather hangs there in the twilight, and comes out the other side and keeps going, into a mirror we've parked above our own atmosphere. And when that light lands, it's carrying a bruise. A few colours are missing from it. And those missing colours are, quite literally, a message about the chemistry of a world we will never visit, never photograph, never touch. Today, how we learned to read it. George, that opening genuinely gives me chills, and I don't fully believe it yet. You're telling me we can figure out what the air is made of on a planet that's a dot we can't even see?
We can. And I love that you don't believe it, because that's the right place to start. The honest truth is that this shouldn't work. The signal is absurdly small. We'll get to just how absurd. But it does work, routinely now, and the beautiful part, Alice, is that everything you need to understand it, you already learned. In a lab, on a homework set. We're not going to introduce a single new law of physics today. We take two things you already trust, press them together, and out the other side falls the frontier.
That's a bold promise. Two things I already know.
Two things. And if anything I say sounds like magic, stop me and make me show you it's just the stuff you know wearing a costume.
Deal? That's basically my whole thing. Two things you already trust.
Here's the first one. Your spectroscopy lab. You take a hot source, a filament, a glowing bulb, and by itself it gives you a smooth rainbow, a continuous spectrum, every color blending into the next.
Right, a black body. Smooth rainbow.
Now put a cooler gas in front of it, a tube of hydrogen, sodium, whatever, and look again. It's not smooth anymore.
There are dark lines, specific colours just gone, like someone took a comb to the rainbow and knocked out particular teeth.
Particular teeth? And which teeth?
Depends on the gas. Each element has its own set. That's the whole point of the lab. You read which lines are missing and say, that's sodium, that's hydrogen. The pattern is a fingerprint.
That's the entire first pillar, and you said it better than most textbooks. The atoms and molecules in the gas can only absorb light at specific wavelengths. The exact energies that match or jump their electrons, or their vibrations and rotations, are allowed to make. Wrong color sails straight through. Exactly the right color gets swallowed. So the missing colors are a signature. And here's the part I want to plant deep, because we lean on it hard later. This isn't a trick that only works in the lab. This is how we know what the sun is made of. Nobody has ever brought back a jar of the sun.
Wait, that's true. We've never been there. We know it's mostly hydrogen and helium because
of the dark lines in its spectrum, named after a fellow called Fraunhofer, who catalogued them in sunlight centuries ago before anyone knew what they meant. Every star whose composition you've ever seen, we read the same way, off the missing colors. So when I tell you we do this for a planet, it's not a new idea. It's the oldest trick in astrophysics, pointed somewhere new.
Okay, pillar 1. Missing colors are chemical fingerprints, and we already trust it enough to have built all of stellar astronomy on it. What's pillar 2?
Pillar 2 is the transit. And you know this one too. When a planet passes directly between us and its star, crosses the face of the star from our point of view, what happens to the starlight we measure?
It dips. The star gets a little dimmer while the planet blocks a chunk of it, then goes back to normal when the planet moves off. A little dip in brightness over time.
And how big is the dip? Don't reach for a number, reason it out. Where does it come from?
It's geometry, right? The planet blocks a fraction of the star's disk, So the fraction of light that disappears is just the area of the planet's little disk divided by the area of the star's big disk. And area goes like radius squared, so it's basically the radius of the planet over the radius of the star, that ratio squared.
That's it. That's the whole formula, and you derived it from nothing but area of a circle. Now let's feel the size of it. Take a giant planet, a Jupiter, crossing a star like the Sun. The radius ratio is roughly 1/10, and you square it. 20.
1/10 squared is 100th, so about 1% of the light disappears. The star dims by 1%.
1%. A big, comfortable signal we were catching from the ground years ago. Now do it for an Earth-sized planet crossing a Sun-sized star.
Earth is way smaller. The radius ratio is something like 1 part in 100. Square that, and you get 1 part in 10,000. So 100th of a percent?
About that. In the units the field uses, that's roughly 80-something parts per million.
Parts per million. Let me feel that because it's going to matter. If a stadium had 1 million light bulbs, 1 part per million is a single bulb going dark. That's the dip an Earth makes.
1 bulb in a stadium of 1 million. 80 odd for an Earth. Hold on to that feeling, because we're about to ask for something even smaller. But first, the honest new step. Everything so far treats the planet as a perfect, hard-edged disk, a clean black coin sliding across a lamp. Challenge that.
A planet with an atmosphere isn't a clean-edged coin. It's got a fuzzy edge. Air.
It's got a fuzzy edge, and that shell of air around the solid body is the whole episode, because that shell is semi-transparent, and crucially, color-selective about it. Put those two words together, semi-transparent, color-selective, and you've already secretly invented the technique. You just haven't noticed. Reading the shadow.
All right, walk me into it slowly because I can feel that there's a move here and I don't want to miss it.
Slowly is right. This is the heart of the whole thing. Go back to the transit and zoom way in on the planet's silhouette against the bright star. In the middle, you've got the solid body. Rock, metal, whatever, totally opaque. That part blocks light, no matter what color it is. That's your main dip, the one you already understand. But now look at the very rim. Wrapped around that solid body is a thin ring of atmosphere. Picture the glowing rim you sometimes see around the moon during a solar eclipse. That halo. An annulus, if we want the fancy word, but let's just say ring.
A ring of air around the edge of the planet. Okay.
And here's the geometry that makes this all possible. Some of the starlight coming toward us doesn't hit the solid body and doesn't miss the planet entirely. It threads right through that ring of air on its way past. It grazes the planet. It goes in through the atmosphere on one side of the rim and comes out toward your telescope, having traveled through a long, slanting path of that alien air.
Oh, so that grazing light is exactly the setup from Pillar 1. It's starlight, a smooth rainbow passing through a gas. So it should come out with dark lines in it, the atmosphere's fingerprints.
There it is. You just fused the two pillars. That grazing light is starlight through a gas cell, except the cell is a whole planet's atmosphere and the source is the star behind it. So it picks up the fingerprints of whatever's in that ring. But now, the cleverest step, watch what those fingerprints do to the transit dip.
Okay, I'm watching.
Pick a color where nothing in the atmosphere absorbs. A wavelength the air is just transparent to. What does the ring of air do to light of that color?
Nothing. It lets it straight through, so at that color the ring is basically invisible, and the planet only blocks light with its solid body. The planet looks its bare rock size, normal dip.
Normal dip. Now switch to a color where, say, water vapor absorbs strongly. One of water's missing teeth wavelengths. What does the ring do now?
Now the ring isn't transparent anymore. At that specific color, the air is opaque. It swallows the grazing light. So the ring blocks light too now, at that color.
So at that color, what's the effective size of the thing blocking the star? Just the solid body, or…
The solid body plus the ring. The planet's shadow is bigger at that color, because the atmosphere, which was see-through a moment ago, is now acting solid.
And a bigger shadow means…
A deeper dip. The transit is deeper at exactly the colors the atmosphere absorbs. Oh, that's gorgeous. So if I measure the depth of the dip at every color…
Then the depth changes color by color. And where does it get deeper? Exactly at the fingerprint wavelengths of whatever's in the air. So you plot transit depth against color, and the bumps in that plot are the absorption fingerprints of the atmosphere. You've measured a spectrum of an alien sky, and you never took a picture of the planet, never resolved it. You watched a star flicker and decoded the flicker one color at a time.
That's genuinely one of the most beautiful ideas I've heard. And it has a name.
Transmission spectroscopy. Transmission because you're using the light transmitted through the atmosphere, the light that passed through it, not bounced off it. And spectroscopy is the part you already owned from your lab. It's just spectroscopy of a shadow.
Let me try an analogy and you tell me where it breaks.
Please, always tell me you're doing an analogy and I'll always tell you where its wheels come off. That's the deal between us and the truth.
On Earth, why is a sunset red? The sun's light near the horizon has to graze through a long, slanting path of our atmosphere to reach my eye, way more air than at noon, and along the way the air scatters and absorbs the bluer light, so what survives is red. A sunset is starlight filtered by a long, grazing path through an atmosphere. And that's the exact same geometry as the grazing light in a transit. The transit is passing through the planet's sunset.
That's a wonderful analogy, and more right than you know. It really is the same grazing, long path geometry, light picking up the character of the air it skims. Here's where the wheels come off in two places. First, in your sunset, you see an actual color with your eye, red. In transmission spectroscopy, we're not seeing a color, we're measuring which precise wavelengths went missing. The fingerprint lines, far more specific than "it looked reddish." Second, and this matters a lot later, the transit light only grazes one part of the planet. The ring around the rim, the boundary between dayside and nightside. The twilight edge. The terminator, if you want the word. So we only ever read the planet's sunset zone, not the whole globe. It's a keyhole. Keep it in your pocket, we'll need it.
Reading a whole planet's sunset, but only its sunset. Got it. Now here's the question nagging me. You keep saying the signal is small. How small? The transit itself was 1% for a giant, 80 parts per million for an Earth, and the atmosphere is just a thin ring on top of that. So its contribution has to be even smaller.
Much smaller. And this is where being honest about the edge earns its keep. So let me not flinch. The dip already exists. That's the solid planet. The atmospheric signal is only the extra depth that appears when the ring goes opaque, a thin rim added to a disk. Its size depends on how thick that rim is, how tall the atmosphere is, compared to the star behind it. Roughly, it scales like the planet's size times the atmosphere's height, over the star's size squared. Put real worlds into that.
Give me the two extremes, the easy case and the brutal case.
The easy case is a hot, puffy gas giant, orbiting scorchingly close to its star, so its atmosphere bakes and bloats and puffs way up, tall and extended. A nice, thick rim. The extra signal there is a few hundred parts per million.
A few hundred out of a million. So out of my million bulb stadium, a few hundred flicker extra at the fingerprint colors. That's the easy case?
That's the easy case. Easy enough that even the Hubble telescope, never built for this, pulled water out of a few giant atmospheres. On one famous puffy giant, water showed up at something like 250 parts per million of extra depth. Comfortable. The frontier of a decade ago.
And the brutal case? Let me guess, an Earth.
An Earth. A small rocky planet has a thin, tight atmosphere. No puffing up, it hugs the surface, and it's orbiting a big star, so that rim is razor thin. The extra signal for an Earth-sized world is around 10 parts per million, sometimes less.
10 out of a million. So the whole question of, is there air on that rocky planet, and what's it made of, comes down to measuring a 10 in a million wiggle in the colour of a star, again and again, through the noise, sure it's real.
That is the frontier, and everything, every headline you've seen about alien air, lives or dies on that razor. A measurement so delicate it barely has a right to exist. Which is the perfect moment for two honest spoilers, two ways this beautiful method gets muddied in the real world. They separate the people who understand this from the ones who just repeat headlines.
Hit me. Spoiler 1.
Clouds and hazes. Everything I've described assumes the grazing starlight goes deep into the atmosphere, samples all those molecules, and comes out fingerprinted. But if the planet has a high cloud deck or a thick haze, the grazing light hits that cloud and stops. It never reaches the deep air where the interesting molecules are. And a cloud is broadly opaque. It blocks all colors, not specific ones. So instead of a bumpy spectrum with clear fingerprints, you get a flat, muffled line, smudged out. And this isn't a rare hypothetical, it's routine. A big fraction of the planets we look at come back partly or fully muted by clouds. It's the most common way the method disappoints you.
So a flat spectrum doesn't mean no atmosphere. It might mean cloudy, can't see in. That's an important difference.
Crucial, and people get it wrong constantly. Flat can mean airless, or flat can mean cloudy, and telling those apart is real hard work. Spoiler 2, you already found yourself. The keyhole. We only read the Terminator, the twilight ring, so we're inferring a whole planet's atmosphere from its sunset zone, which might not represent the roasting day side or the frozen night side at all. A keyhole view, not a portrait.
Clouds smudge it, and it's only a keyhole. So given how brutal this is, 10 parts per million, moody stars, clouds, what changed? Why are we suddenly able to do this at all? You're clearly building toward, and then something happened.
Something happened, and its name is the James Webb Space Telescope. And let me be precise about why it's the game changer, because it's not just big telescope hooray. 3 things. First, it works in the infrared, light at wavelengths longer than your eye can see. That matters enormously because most of the molecules we care about, carbon dioxide, water, methane, sulfur dioxide, sing their strongest, cleanest fingerprints in the infrared. In visible light, their signatures are faint and tangled. In the infrared, they're loud and clear. Second, it's above our own atmosphere, in space. Essential because our own air is full of water and carbon dioxide. Try to look for water on an alien planet through Earth's water-soaked sky, and you're hopeless. You have to get above our own fingerprints to read someone else's. And third, it's simply enormous. A huge mirror, which buys the precision to even dream of a 10-part per million measurement. Infrared, above the atmosphere, and huge. That's why the last few years feel like someone finally turned the lights on. What we've actually read.
So let's talk about what we've actually read with it, and I want you to keep doing the honest thing. Tell me what's rock solid versus what's shaky.
I'll hold that line the whole way, because this is the topic where it matters most. Start with the cleanest, most solid result, the one that made the whole field exhale. Summer of 2022. Webb pointed at a planet called WASP 39b, just a catalogue name. It's a hot Saturn, about Saturn's mass, but puffed up by its star's heat until it's wider than Jupiter, orbiting scorchingly close to its sun, roughly 700 light-years away. A big, puffy, easy target, the friendly case.
The thick whim, few hundred parts per million case, the easy one.
The easy one, chosen precisely because it was easy. You prove a new method on a soft target first. And Webb read its transmission spectrum and saw, unambiguously, carbon dioxide. The first clear, definitive detection of carbon dioxide in the air of a planet around another star. And when I say definitive, I mean it strictly. The confidence was so overwhelming that the chance it was a fluke of the noise was, for all practical purposes, 0. This wasn't a hint. This was a signature standing up out of the data and waving.
So this is the "we can read any alien sky now" moment. Not "is there air," but "we can name the molecules."
That's the milestone. Proof of the whole concept, clean, no asterisks. And then the same observations gave us something even better. In that same atmosphere, they found sulfur dioxide. And here's why chemists sat up. That sulfur dioxide can't be left over from when the planet formed. It has to be manufactured on the spot, built by the star's own ultraviolet light, driving reactions in the upper atmosphere. Photochemistry.
Photochemistry, light-driven chemistry, like how sunlight makes ozone in our own atmosphere.
Exactly like that. And it was the first time we'd ever caught photochemistry happening on another planet. Think about that. We didn't just take inventory of what's present, we caught the atmosphere in the act of doing chemistry, making something new. These alien skies aren't static balls of gas, they're dynamic chemical factories reshaped by their star in real time. We went from what's there to what's happening. That's when it stopped being a party trick and became a science.
Okay, that's the triumphant part. I can hear the "but" coming.
You can always hear it coming. That's why you're good at this. Here's the but. Everything I just praised was a big, puffy, hot giant. The easy case. But nobody dreams about giant planets. What do we actually want to find?
Rocky planets, Earths, places you could imagine standing on, places that could, maybe, host life.
Right. And rocky planets are the brutal case, the 10 parts per million case, thin, tight atmosphere, the razor's edge. So the real test of this era isn't the giants. It's whether we can do this for small, rocky worlds. And the marquee system for that, the one everybody's watching, is called TRAPPIST-1.
I've heard of this one, the one with a bunch of Earth-sized planets.
7 of them. 7 roughly Earth-sized planets packed tight around a tiny, cool, dim star. An ultra-cool red dwarf, only about 40 light-years away. Announced back in 2017 and an instant sensation because 3 of those 7 sit in what we call the habitable zone. It's the most studied planetary system we have, other than our own.
Hold on, habitable zone. Define that carefully because I have a feeling it doesn't mean what it sounds like.
I'm glad you stopped me, because this is one of the most misunderstood phrases in science. The habitable zone is purely about distance and warmth. It's the band of orbits where a rocky planet could, in principle, hold liquid water on its surface if it had a suitable atmosphere. That's the whole definition. It says nothing about whether the planet actually has water, or air, or life. Habitable zone is not the same as habitable, which is not the same as inhabited. 3 different claims.
So, in the habitable zone just means the right distance for the temperature to be okay, in principle. Not has oceans. Not has anything.
Not even has air. Here's the example that should burn it in. Venus. Venus sits right at the edge of our own sun's habitable zone. And Venus is a runaway furnace, hot enough at the surface to melt lead, crushing pressure, clouds of acid. technically in the zone, absolutely not habitable. So every time you hear a planet in the habitable zone, translate it to a planet at a promising distance, and we know essentially nothing else.
That reframes everything. So Webb points at these rocky TRAPPIST-1 planets, the whole dream, and finds what?
A sobering reality check. Take the innermost planet, TRAPPIST-1b. Webb measured it carefully, a slightly different technique there, reading its heat, but same spirit. And the results are consistent with a bare, airless, dark rock. No thick atmosphere. They ruled out any substantial blanket of air, just rock baking in starlight.
Airless.
Looks airless. And the next one out, TRAPPIST-1c, they ruled out a thick carbon dioxide atmosphere like Venus has. Only a thin one, or none, remains possible. So the pattern for these inner rocky planets is thin at best, quite possibly no atmosphere at all. Bare rock.
That's kind of heartbreaking. The dream system and the planets might just be bald rocks.
It is, and I won't sugarcoat it. But here's why it's profound, not just a letdown. There's a cruel irony. The very thing that makes these planets easy to study, orbiting a small, dim red dwarf, deep, frequent transits, is the same thing that may have killed their atmospheres. Red dwarfs are violent when young. They flare, they blast out radiation and stellar wind, and a small planet hugging close can have its air stripped away over time, blown off into space. So the settings that let us see rocky planets clearly may be the ones least likely to let them keep their air. Whether rocky planets around red dwarfs hold onto atmospheres at all is a live, genuinely open question. Nobody knows. TRAPPIST-1 is currently voting, often not.
And before we go further, you said thousands of planets. How many worlds are we even talking about?
More than 6,000 confirmed now. And I'll be careful with that number. People love to quote it too precisely, but the real count ticks up basically every week, so the honest figure is more than 6,000, not an exact tally. And that's out of what we believe are billions in our galaxy alone. There's a lovely human story under that number too, because this field is young. The first planet ever confirmed around an ordinary star like our Sun, a normal Sun-like star, was found in the year 1995. It's called 51 Pegasi b. Two astronomers in Switzerland, Michel Mayor and Didier Queloz.
1995. That's not even that long ago. That's within a lot of our listeners' lifetimes.
Within living memory. Before that, we knew of exactly 0 planets around normal stars, just our own solar system and a lot of philosophical hope. And let me be precise, because precision is the whole ethic here. 51 Pegasi b was the first around a Sun-like star. There were a couple of even stranger worlds found a few years earlier around a dead, collapsed stellar corpse, a very exotic setting. So 51 Pegasi b isn't quite the first exoplanet ever. It's the first around an ordinary star like the Sun. That's the one that opened the floodgates, and Mayor and Queloz shared the Nobel Prize in Physics for it in 2019. So in one human career, we went from 0 planets around normal stars to more than 6,000 to reading their atmospheres. That's the pace of this thing.
From 0 to reading their skies in one lifetime. So, we can read any sky, we've caught chemistry happening, we're pushing on rocky worlds. Which brings us to the question everyone actually wants to ask, and I've been holding it in the whole time.
Ask it.
Can we detect life? The word we haven't found.
Now you get to watch me be as honest as I've ever been, because this is the exact spot where the field's discipline is being tested in public, right now. What would we even look for? We can't see aliens, we can barely see the planet. What we can read is the air. So the question becomes, is there a gas, or a set of gases, whose presence is really hard to explain without life? We call that a biosignature.
A biosignature, a gas that shouldn't be there unless something living is making it.
That's the dream version of it, yes. And the poster child is oxygen. Our own air is about a fifth oxygen. And here's what makes it promising. Oxygen is reactive. It wants to combine with things. Rust, fire, rock. Left alone, it should slowly vanish into the surface. The only reason Earth's air stays loaded with it is that life, photosynthesis, keeps pumping it out faster than it's removed. So the reasoning goes, find an Earth-like planet, see a big oxygen fingerprint, and you found something fighting chemistry to stay there. Something must be replenishing it. Life.
That sounds airtight. Honestly, the whole game. See oxygen. Done.
It does sound airtight. And now the twist that keeps careful scientists up at night. A biosignature can lie. Oxygen, the best one we've got, has innocent, lifeless ways to build up. No biology required.
Wait, how? You just told me oxygen should disappear on its own.
On a planet with life keeping the balance, sure. But picture a different planet. Lots of water, and a star blasting it with strong ultraviolet light. That light can split water molecules apart, high in the atmosphere. Water is 1 oxygen and 2 hydrogens. Break it, and the hydrogen is so light it can escape the planet's gravity and leak off into space. And what's left behind when the light hydrogen floats off?
The oxygen, the heavy part, stays. So you pile up oxygen just by breaking water with starlight and letting the hydrogen escape. No life anywhere.
No life anywhere. That's a false positive, a signal that mimics the thing you're hunting for, but has a boring, dead explanation. And it's not the only route. Certain planets with the wrong history can brew oxygen without any biology. And that reshapes the whole modern view. Nobody serious believes anymore that a single gas proves life. Not oxygen, not anything. What you need is context, the right combination of gases together, ones that shouldn't coexist unless something's continuously making them, on a planet where you've ruled out every innocent explanation. The community has literally written formal standards of evidence for how paranoid you must be before you're even allowed to whisper the word life. That paranoia isn't weakness. That paranoia is the science.
Okay, so with all of that as the backdrop, the false positives, the standards, the paranoia, there's a specific planet that's been all over the news. I have to ask about it because everyone's heard the headlines. K2-18b.
I was waiting for it, and I'm glad it's you asking. This is the most important cautionary tale in the field right now, and it's a detective story with, hold this, an unresolved ending. No bow. The planet. K2-18b is a sub-Neptune, bigger than Earth, smaller than Neptune. About 2.5 times Earth's radius, 8 or 9 times its mass, roughly 120-odd light-years away, going around a red dwarf on an orbit of about a month, and it sits in that star's habitable zone, which, as you now know, means only promising distance, nothing more. Its density is genuinely in between a rock and a gas world, so we honestly don't know what kind of planet it even is. Ambiguous from the start.
Ambiguous is a good word to keep in mind, I'm guessing.
Keep it lit up in neon. Now the story. 2023, Webb found methane and carbon dioxide in its atmosphere, and notably no ammonia. And one team, LED by an astronomer at Cambridge, read that combination as consistent with a Hycean world, a made-up word, hydrogen plus ocean, meaning a possible water ocean under a thick hydrogen sky. And in that same data, they reported a weak, tentative hint of another gas, dimethyl sulfide.
Dimethyl sulfide. Why does that one matter?
Because on Earth, dimethyl sulfide is made almost entirely by life, mostly marine plankton. It's part of the smell of the sea. So the suggestion hanging in the air was enormous. A possible ocean world, with a gas that on Earth means plankton. You can see why it detonated in the press.
Oh, absolutely. Ocean planet, smell of the sea, sign of life. That writes its own headline.
It writes its own headline, and that's exactly the danger. Now, spring of 2025, the same team came back with more web data, this time from the mid-infrared, and reported stronger evidence for dimethyl sulfide, maybe along with a chemical cousin of it. And the confidence they quoted was around what physicists call 3 sigma. And now I have to teach you the single most important idea in this whole episode, even though we're saying no numbers.
The sigma thing? Translate it for me because I hear 3 sigma, and I don't have a feel for whether that's a lot.
Sigma is just a way of saying, how unlikely is it that this is a random fluke of the noise? 3 sigma means, if there were really nothing there, you'd see a bump this big by pure chance only about 3 times in 1,000. Fairly unlikely to be an accident. Sounds impressive, right?
3 in 1,000? Yeah, that sounds pretty convincing to me, honestly.
And here's the discipline that makes physics physics. 3 sigma is not a discovery, not close. The bar the field demands before anyone calls something a real detection is 5 sigma. And that's not a bit more, it's a completely different universe of certainty. 5 sigma means the odds of a fluke drop below about 1 in a million. Not 3 in 1,000, 1 in 1.5 million. That's the gold standard, and it exists for a brutal reason. 3 sigma signals evaporate all the time. The history of physics is a graveyard of exciting 3 sigma bumps that more data quietly erased. They're the normal weather of the edge. A 3 sigma hint is a reason to look harder. It is not a reason to announce anything.
So even the team reporting it, they weren't claiming they'd found life.
To their credit, they framed it as evidence to be tested, not proof. And NASA said it about as plainly as an agency ever does. A single potential biosignature would not, on its own, constitute the discovery of life. Full stop. But here's where the detective story turns. The pushback from the rest of the field was fast, strong, and from several directions at once.
Independent teams went and checked.
The immune system of science working exactly as designed, and I find it genuinely beautiful. One group combined all the web datasets on this planet, reanalyzed the whole thing, and concluded there was insufficient evidence for dimethyl sulfide. Another wrote a paper with a title so blunt it's almost funny. Essentially, this planet does not meet the standards of evidence for life. A separate NASA LED reanalysis also found no conclusive evidence. And it gets deeper. Some reanalyses found the wiggle could be fit just as well, or better, by completely different molecules. So the fingerprint might not even be dimethyl sulfide at all. The identification itself is shaky before you even get to the life question.
So it might not be dimethyl sulfide, and even if it is,
dimethyl sulfide is a leaky biosignature anyway. Same problem as oxygen. Lab experiments and observations show it can form without any life at all through ultraviolet chemistry. It's even been detected on a comet and in cold clouds of gas between the stars, where there's definitely no plankton. So some very well-respected scientists say it shouldn't be treated as a reliable sign of life in the first place. As one put it, the temptation to over-interpret is enormous. And that whole Hycean ocean world picture is just one interpretation. Other researchers fit the same data with a boring, hot, gas-rich mini-Neptune with no habitable surface at all. No ocean, no plankton, just a warm ball of gas.
So let me try to say the honest state of it, and you correct me. We have a genuinely interesting planet. A 3 sigma hint, below the bar, of a gas that might be dimethyl sulfide, but might be something else entirely. Independent teams couldn't reproduce it and don't buy it. The gas, even if real, can be made without life. And the ocean world story it's attached to is itself just one contested guess. So the honest summary is exciting, worth watching, and absolutely definitely not a detection of life.
That's exactly right, and you said it more carefully than most of the coverage did. As of right now, the dimethyl sulfide claim on K218b is contested, unconfirmed, and not accepted by the broader community as evidence of life. And more broadly, the sentence I most want to leave you with: no biosignature, and certainly no life, has been confirmed on K218b or on any other planet anywhere. Full stop. We have not found it.
And here's what surprises me. You're saying all that not with disappointment, but almost with pride?
With pride. Because look at what happened. A team saw something tantalizing and reported it, honestly, with its uncertainty attached. And the rest of the field didn't cheer. They descended on it, poked every hole, and said, "Not good enough, not yet." That's not the system failing. That's the system working perfectly. The power of the K218b story isn't a discovery. It's that it shows you what real science at the frontier looks like from the inside. A thrilling signal, a chorus of disciplined doubt. We need more data, said out loud by everyone, without embarrassment. That restraint, the refusal to claim the thing we most want to claim, is itself the frontier.
So where does that leave a student who's listening and thinking, I want to work on this? What's actually open?
So much, and that's the gift of your timing. 1. The whole false positive problem is unsolved. How do you build a rigorous, statistical, chemical case that a gas really requires life, ruling out every innocent story? Nobody has a finished answer. That's a career waiting for someone. 2. Can rocky planets around red dwarfs even keep their atmospheres? TRAPPIST-1 is whispering, often not, but we don't know, and it decides whether the most common planets in the galaxy can be alive at all. 3. The machines. Webb is pushed right to its limit on rocky worlds. It can just barely reach a favorable Earth-sized target at that 10 parts per million razor. There are future observatories being designed right now, on paper, specifically to hunt for oxygen with context on true Earth twins. They don't exist yet. Someone listening might build them.
I keep coming back to the fact that all of this, reading the air of another world, is a thing humans literally could not do when a lot of us were born.
That's the part I never get over. A single lifetime ago, 0 known planets around normal stars. Then thousands. Then, just a few years ago, the first clean reading of carbon dioxide in an alien sky, and the first time we ever caught another planet's atmosphere doing chemistry. We have, genuinely, learned to read alien skies. That's done. That's real. That's not hope. That's proved. What we have not done, not once, not anywhere, is read the word life in any of them. And the most honest, most exciting thing I can tell you is that the discipline of not claiming we have, when every human instinct is screaming to, that restraint is the frontier. The tools to finally ask the question exist for the first time in the history of our species. And the question is wide, wide open. That's not a story that ends. That's a story waiting for you to pick up.
We've learned to read the sky, we just haven't found the word yet. That's the most honest and the most hopeful place we could possibly stop. George, thank you. This one's going to stay with me.
Keep looking up. And keep doubting, both at once. That's the whole job.